in form of shearing. So that tends to create shearing within the rock. So there will be fracture under shearing during the traveling time of the shock wave within the rock mass. So some of the cracks tends to formed under fracturing, under shearing. So some of the waves fails the rock under shearing. Then at the crushing zone, some of the rock fails and gets crushed under compression. So the last medium of fracturing is the tensile stress. The tensile stress. So how did the rock tends to fail and create cracks? Let's assume this is the rock mass. This is the free face. This is the zone. So some of the rocks tends to fracture under tensile, under shearing. Then we all agree the wave is still traveling. Some has fractured the rock, some at this point has reflected, some at this point in the case where there is existing fracture, some of the waves have tends to fill this place, increase the aperture of the hole. Some of the waves are still traveling. On getting to another medium, this is the free face, this is solid, this is here. On getting to another medium, the wave tends to reflect, tends to travel back. As I said earlier, all this cracking, all this fracturing occur within the time of shock wave traveling and gas energy release. So as all this fracturing is taking place, the components of the explosive which has been disintegrated tends to react within each other, react with one another to produce the gas energy. So before the gas energy is being produced, the shock wave perform this operation, the fracturing under compression, fracturing under shearing, fracturing under tensile. So I've explained compression, which is the crushing zone. I've explained the shearing, then explaining the tensile stress. How did the rock tends to fracture under tensile? So what happened is that when the shock wave being released by the explosive at detonation tends to travel and get to another medium. This is what makes blasting perform with one or more free face, tends to yield more than those that is being performed with a single free face in the form of crater, with a single free face whereby the only horizontal face is the only free face. This is the reason why most blast design is designed in such using burst cut, so that there will be creation of additional free face. But in the case whereby the only free face is at horizontal, all this place blocked. The only available free face is one horizontal. This tends to be limited. Then you have poor blasting as a result of that. So when the shock waves, after performing the crushing, the shearing, the compression, then gets to the free face, interacts with another medium. Then after interacting with another medium, then it travels back. It tends to reflect back into the rock mass. Believe me, the wave is traveling like this at this direction, then another reflection at this direction. This tends to, assuming this is the each rock grains, this tends to shear, this tends to cause a tensile stress to be developed within the rock grains. The wave coming back, the reflection wave coming back, then the wave traveling like this. This tends to create slabbing This tends to create slabbing in the principle with alignment with the principle of tumbling failure in rock. Tumbling failure. Rock tends to slab long. So this at this point, where the wave, the traveling, the reflected. So at this point, this tend to fracture under tensile. So after all the microfractures has been created, the rock has been fractured, then here comes the gas energy. The gas energy is the gas energy, according to scholars, did about 85% to 90% of the whole rock fragmentation. It performed the explosion. It exploded. Since I mentioned earlier, the shock waves only fractures the rocks. So it creates fractures. So the gas energy filled the fractured, then cast throw the fragment. It tends to throw the fragment, cast it to the available free face. So I think during blasting, shock wave is released. The shock wave fractures by compression, by shearing, by tensile stress. So after fracturing, the gas energy explodes the rock mass. What tends to makes most blasting failed is that in a case where there is insufficient micro cracks, the shock wave released by the explosive refuse to create enough micro fractures that will make the burden on the gas energy to be lesser. Then in such case, more of oversized material will be produced. Let's see. Okay, this is the free face, this is the rock mass, this is the drill hole. Assuming this is the drill hole, at this point, without shock waves, it will be very difficult for the gas energy released to cast the whole of this rock mass. It is highly impossible. Rather, the gas energy will tend to blow out. It will blow out. All the energy will be released vertically because the burden here is too heavy and the rock mass is attached to another bedrock. So the gas energy is not sufficient. It's not sufficient to fracture the rock, but it's only sufficient to throw the rock. So what happened is that the drill hole, then the shock wave fractures the rock at different dimensions, fractures the rock. Some tends to fail under shearing, the crushing zone, the tensile slabbing. So this rock is already fractured. It has been broken down into different sizes. So and there's discontinuity, within the rock mass. This tends to be particle 1, particle 2, particle 3, particle 4, particle 5, particle 6, like that. So the gas energy being released after the fracture tends to throw each at each direction, cast particle 1, particle 2. So it's easy to move each particles compared to the rock mass. So as I've explained, the shock wave only fractures the rock, but the gas energy, the shock wave did 10 to 15% of the rock fracturing, while the gas energy performed 85 to 90% of the rock fracturing. So in most cases whereby the fracture is not sufficient, the gas energy, in addition to throwing the rock, tends to fragment the rock further at casting. Like for example, this is a rock mass. This is a rock mass that has been fractured, but at casting was casted like this. On getting to this floor, it tends to fragment. So there is still possibility of breakage within the rock during casting during piling. So during the throw, some of the rocks that have been fractured, if properly fractured, tends to still break at casting. So I've covered what the topic is said to entails, and I would like to stop here so as to reduce the length. And so I want to thank everyone. I've covered the release of shock waves, the release of gas energy. Most importantly, I've explained what happened during detonation, the whole column. This is the charge length. This is the charge length, the stemming. So sometimes maybe the subdrill. So the charge length, then the surface initiator shock waves travels to the primer, to the booster, to all of the charge. At detonation, boom, there's release of shock wave. Shock waves travels, there's a free phase. The shock wave travels between this point to this point at time delta d, delta t. So within this delta t time, the shock wave, the shock energy in the medium of wave fractures the rock mass, create fractures. But in a case whereby the traveling time of the shock wave, this is where the effect of burden comes in. Effect of burden. In a case whereby the design burden is too much, the burden is overestimated. The given burden, that is the distance between the last hole to the free phase, is too much, thereby taking much time for this wave to travel. That is, the wave travels, leave the detonation point to the free phase, and yet to return back to the free phase before the release of gas energy. Then that means the wave has created tensile slabbing, but due to large burden, before getting back to the detonation zone, the gas energy has been released. Only this section will be well fragmented. Then you have this as an oversize. So I'm trying to explain the effects